Ever wonder why a rumor can sweep through your entire office by lunchtime? Or how you might actually, literally, be just a few handshakes away from anyone on the planet? Well, today, in this explainer, we're mapping out the hidden math of human relationships. We're going to dive deep into social network analysis to uncover the invisible architecture that dictates how information, resources, and influence actually flow through our lives. We'll start small by zooming in on individual connections, and then we're going to zoom all the way out to massive global webs. Okay, here's our roadmap. We'll hit the anatomy of networks, the strength of weak ties, the small world phenomenon, identifying key influencers, and finally, maximizing information diffusion. Let's get into it. Section 1. The anatomy of networks. We have to start our journey at the absolute smallest level before we can understand how things go viral. Think of nodes as the fundamental building blocks of any network diagram. When we're talking about social network analysis, or SNA, we represent the specific entities we're looking at as nodes. So, depending on what we're measuring, a node could be a single person on a social platform, like you. Or it could be a whole department in a massive corporation, or even an entire country. Now, when you draw a line between two of those nodes, boom, you've just created a measurable social network. We call these lines edges or sometimes ties. They represent the actual interaction. Maybe it's a friendship, a financial transaction, or just a flow of information. And what's cool is these edges can carry different weights to represent the emotional intensity or how frequently that interaction happens. And looking at these edges reveals a massive core quirk of human behavior, homophily. It's literally the sociological version of birds of a feather flock together. We just naturally form tight, dense clusters with people who look, think, or act like us, whether that's based on our jobs, our education, or our shared values. Section 2. The strength of weak ties. Let's zoom out a bit and see how these dense little groups actually connect to one another. Okay, get ready for a wild paradox in network theory, courtesy of sociologist Mark Granovetter back in 1973. Here it is. Your absolute closest friends, your strong ties, are actually terrible for spreading new information. I know it sounds backward, but think about it. You all know the exact same people. You're exposed to the same ideas and the same news. It's actually your weak ties, like the barista you chat with or that distant coworker from another department, who give you access to completely novel information and opportunities, purely because they travel in totally different social circles. To prove this mathematically, Granovetter looked at something he called the forbidden triad. It goes like this. If you're best friends with Bob and you're best friends with Alice, it is highly, highly unlikely that Bob and Alice don't at least know each other. We basically assume this forbidden triad almost never happens in reality. What that means is strong ties inevitably cluster into closed, redundant loops. Because strong ties form those closed echo chambers, it's actually those infrequent acquaintances, our weak ties, that end up acting as vital local bridges, connecting completely isolated sectors of a network. Think of it this way. If you remove a strong tie, the network probably stays intact. But if you sever a weak tie, you might completely cut off the flow of information between two entirely different groups of people. They are incredibly powerful. Moving to Section 3, the small world phenomenon. Time to zoom way out to the global web of humanity. Back in '98, Duncan Watts and Steven Strogatz built this brilliant mathematical model that proves how a network can be super cliquish locally, but globally connected by incredibly short paths. It beautifully marries the two concepts we just covered, highly clustered local groups, punctured by these random, far-reaching bridges created by weak ties. Yup, this exact dynamic is the math behind the famous 6 degrees of separation phenomenon. Because of these long-reaching weak ties, you can navigate a massively decentralized network and reach practically anyone on Earth through a surprisingly short chain of acquaintances. It's a small world, mathematically speaking. Section 4. Identifying key influencers. So now that we have our map, who actually matters most in this structure? It turns out true influence comes in 4 distinct mathematical flavors. It's not just about raw popularity. Degree centrality is exactly that, though, the popular kid, just measuring your direct friends. But then you have betweenness centrality, which makes you the gatekeeper, bridging different groups. Closeness centrality makes you an efficient broadcaster because you have the shortest path to everyone. And eigenvector centrality, that means you might not have a ton of friends, but the friends you do have are absolute VIPs. Taking this a step further, sociologist Ronald Burt coined structural hole theory. If you look at a network map and spot a totally empty space, a lack of ties between two groups, that's a structural hole. By positioning yourself as the sole bridge across that gap, you completely control the flow of resources and ideas between those two groups. It grants you immense strategic advantage because you literally dictate what information crosses that void. Okay, so we've built the static architecture. We know the nodes, the ties, the influencers, but a network is a living, breathing thing. How does a message actually catch fire and go viral? Section 5, Maximizing Information Diffusion. Let's look at the actual algorithms behind the word-of-mouth effect. These two models mathematically simulate how we change our behavior. In the linear threshold model, humans act on peer pressure. Think about it. You usually only buy a new gadget when a specific critical mass of your friends have bought it, right? On the flip side, the weighted cascade model is all about sheer exposure. Every single time a friend adopts an idea, it flips a mathematical coin determining if you'll cave and adopt it too. This sets up the ultimate challenge for marketers and public health officials alike, the influence maximization problem. Imagine you have a tiny budget. You can only give away free product samples to, say, K number of people. Finding the absolute best starting nodes, the ultimate seed set, to trigger the largest possible cascade across the network is a tremendously complex mathematical puzzle. Finding that absolutely perfect seed set is computationally NP hard. Actually, it's basically impossible for a computer to solve perfectly in a reasonable amount of time. But a researcher named Kempe proved we can approximate it. By using a hill-climbing strategy, where an algorithm iteratively picks the next best node based on thousands of randomized Monte Carlo simulations, we can guarantee a result that gets incredibly close to perfect. Ultimately, influence is a science of structure, not just charm or popularity. To wield real power in your industry or your community, stop obsessing over counting your friends. Instead, look closely at the map, find those empty spaces, and ask yourself, what bridges are you going to build?